There are certain problems in physics that everybody just does at some point. So the bathroom scale on an elevator is one problem like that. The Atwood machine is another. And really there's a few different variations of the Atwood machine that you might see. And I have other videos that deal with some of the other variations. But for this one, let's just look at the basic Atwood machine and how to think about solving this type of problem. So the basic setup on this, and what makes it different from some of the other problems we worked earlier, is that there are two objects that are both moving that we have to track. And their motion has something in common because they're tied together by this string. So that's going to be important in our work. But that's the trick here, is now we're not just doing one object, we're doing two of them. So we'll give one a little bit more mass than the other one. We'll throw the rope over a pulley here, we'll let them go, and the more massive one is going to accelerate downward, and the less massive one is going to accelerate upward. And so here we're asked to find the acceleration of those blocks. You might also be asked to find the tension, or once you find acceleration, you could find something like a velocity or a displacement. Any of those kinematics quantities could go in here as well. So how do we think through this? Well, we've got masses. We've got some evidence that we might be doing something with forces here. We could figure out a force of gravity. There's a rope there, so we have a tension force. And we're asked about acceleration. This problem should scream Newton's second law to us. And second law problems, we always start with a free body diagram. But here we have two objects. That means two free body diagrams and two Newton's second law equations, one for each object. So I'm going to divide my workspace up a little bit here and have some space for block A and some space for block B. And then I'll start with a free body diagram. Block A has gravity pulling it downward. And I'll label that FGA just to distinguish it from the other gravitational force we'll have here. And then we've got a tension force upward. As far as magnitudes go here, that tension force I know must be smaller than my gravitational force because that's my 3 kilogram block. That's the one that's going to be accelerating downward. So my downward force must be bigger than my upward force. Now block B also has gravity downward, but it's not going to be as much as on A. It's only got a third of the mass, so it'll have a third of the gravitational force. And then it's going to have tension upward. On it as well, and we know that that tension force is going to have to be bigger than the gravitational force because block B is going to have to accelerate upward. Now there's one other thing we can say here, and that is the tension force on A and the tension force on B. What's the relationship between those magnitudes? Well, it turns out that those will be exactly the same. Some of these problems might specify that we have a light or a massless rope, also that it's a non-stretching rope. They might also specify a light and frictionless pulley, and all those things are basically to get us to the idea that the two objects that are interacting are blocks A and blocks B. The string or the rope there allows those two to interact, but it is an indirect interaction between block A and block B. And so Newton's third law says that when we have two objects interacting, they each get a force. And those two forces are equal in size and opposite in direction. So why aren't these tension forces opposite in direction? Well, that's what the pulley does. The pulley changes the direction of the rope, which changes the direction of the tension force. So if I had block A right here, we'd have a tension force on block A that pulled it downward, and a tension force on block B that pulled it upward. In general here, until we get to rotation and we have massive pulleys or friction-y pulleys, we'll say that the tension anywhere along a rope is the same. So it doesn't matter whether we're looking at point A or point B or somewhere in the middle, the tension is going to be exactly the same. And so what that means for us in our problem here is that we don't need to distinguish A from B for our tension forces. Those are going to be exactly the same size. Then I can write a Newton's second law equation for each of these. So acceleration for A equals net force on A divided by the mass of A. And acceleration for A then will be equal to our tension force plus the gravitational force. That's on A divided by the mass of A. And over for block B, acceleration for B equals the net force on B divided by the mass of B. And so acceleration for B here will be equal to our tension force again, plus the gravitational force on B divided by the mass of B. Now when we think through the possibility of putting in numbers here, I've got, masses are given to us in the problem, so 3 kilograms for A, 1 kilogram for B, so we're good there. Gravitational forces, I don't know the values for those just yet, but I do have this expression, force of gravity equals mass times acceleration due to gravity. And so acceleration due to gravity we'll assume is 9.8 here, 9.8 meters per second squared downward if we're on Earth. So we could plug in the mass and the 9.8 value there to get the force of gravity for each object. So we'll have 3 times the force on block A that we do on block B. And then we kind of get stuck here. We don't have a tension force. We don't have an acceleration for A. Over here, same problem. We don't have the tension force and we don't have the acceleration for B. So what do? Well, we need to recognize that these accelerations are going to be equal to each other but in opposite directions. The fact that we are dealing with two objects that are tied together means that they have to move together as well. So I can write an equation that kind of spans the gap of these two, that acceleration for object A has to be equal to the opposite of the acceleration for object B. So if B is accelerating upward at some rate, A must be accelerating downward at the same rate. And then once I recognize that, I see that I can plug in this expression here for acceleration of object A, and this expression here for acceleration of object B. And then we'll end up with an equation that has just the one unknown in it. It's going to be the tension force. That's our unknown. And from there we can solve for a tension force, which means we can eventually get to acceleration. So that's our approach. Let's finish it up here. So force of gravity on object A, that's going to be the 9.8 meters per second squared times 3 kilograms, so that's 29.4 newtons. And on object B, we'll have 1 kilogram times 9.8 meters per second squared, so that'll be 9.8 newtons on that one. All right, and so I'll plug in numbers here as I'm making this substitution. So I have, force of tension plus force gravity A, that's 29.4 newtons, and it's downward, so I'll make that a negative 29.4 newtons, divided by the mass of A, which was 3.0 kilograms, equals negative, and then force tension, plus, and then force of gravity on B was 9.8 newtons down, so negative 9.8 newtons, divided by the mass, that was 1.0 kilograms for that box. From here we need to isolate Ft. I'm going to multiply both sides by 3 kilograms first, so that leaves me with Ft minus 29.4 newtons equals, and then I'm also going to factor or distribute that negative sign while I'm multiplying by 3. So this will be negative 3 kilograms times Ft. And you know what? Let's actually just cancel out the kilograms here. When I multiply both sides by 3 kilograms, the kilograms will cancel out. So let's just make that negative 3 times Ft plus 9.8 times 3 is 29.4. And now it's just divided by 1 instead of by 1 kilogram because I multiplied both sides by kilograms here. So we have no more denominator at this point. Okay, then I've got negative 3 Ft on the right side, so I'll add 3 Ft to both sides. That gives me 4 Ft on the right side. And then I'll add 29.4 newtons to both sides here, and so that's going to give me 58.8 newtons. And so then my tension force, I'll do 58.8 newtons divided by 4. And that gets me 14.7 newtons. Okay. Now, a good check when you're solving a system of equations in general is to take whatever value you got first and plug it into both equations that you use to get there and make sure that you get answers that make sense here. So I'm going to take that tension force and I'll plug it in here to figure out what acceleration I get, and I'll plug it in again here to figure out what acceleration I get, and we should get the same acceleration for each object, just with a different sign on those. So let's make sure that that is what we get. So we'll do acceleration for A. Okay, there we go. Equals Ft, that was 14.7 newtons, plus a negative 29.4 newtons, divided by 3 kilograms. And so we get acceleration for A equals 14.7 minus 29.4 divided by 3, and that's negative 4.9 meters per second squared. And then acceleration for B will be equal to 14.7 newtons plus force of gravity on that one, so that was negative 9.8 newtons divided by 1 kilogram. And let's see, 14.7 minus 9.8, that's 4.9 divided by 1. 4.9 newtons divided by 1 kilogram gets us positive 4.9 meters per second squared. And those are going to be our final answers. So they should be the same size in opposite directions, and they are, which is a pretty good check that we did our algebra correctly here. So, key facts to keep in mind about Atwood machines. The tension force is the same anywhere along the string. So they're both attached to this string. They both receive the same size force. The pulley can change the direction of that force, making it upward on both of these instead of in opposite directions, like Newton's third law would normally predict. But we still have a third law pair here. Also important to keep in mind, as long as the string is not able to stretch and as long as it's not breaking, they have to move together. So if A moves down by a meter, B has to move up by a meter. If A is accelerating downward at a meter per second squared, B has to be accelerating upward at a meter per second squared. So those two accelerations have equal magnitudes, just in opposite directions. Those two facts are going to be enough to let us set up a system of equations, which we can then solve to find the tension force in that rope and therefore the accelerations on both objects. As I said, there's a number of variations on the Atwood machine, but they all have the same basic principles that we're looking for. And so they may throw in things like friction, having friction between surfaces involved in this. The modified Atwood machine, we have one of these blocks sliding across a table instead of hanging down from a string. But they all employ the same basic ideas. Thanks very much for watching. If you learned something from this, I'd love to see a like or a comment or a subscription from you so you can see videos in the future. Thanks again. Take care.